Alright, let's get started with today's first problem. This is LeetCode number 658, find k closest elements. Given a sorted integer array R, two integers k and x, return the k closest integers to x in the array. The result should also be sorted in ascending order. Okay. So, let's see. So our input is, let me just clarify this. So we have an integer array, an integer x, and then the output should be a list of integers which in ascending order are closest to x, and the number of integers, so size k, of integers which are closest to x. Okay. And, okay, let's see. That makes sense. N, which is number of elements, is less than or equal to 10 to the 4, which seems to suggest either O of n or O of n log n solution, which seems to make sense. So let's see. I think the brute force solution would be to start by sorting the entire array. Then after you sort the entire array, what you'll do is that you'll find the element within the array. You could use a binary search for this. So this would take O of n log n time. The binary search to find the element that we want, which is x, is O of log n. Then we can say starting at, let's see. How would we do this? I'm thinking about getting the k closest elements. In that case, the closest would be the closest would be the closest values in terms of indexes, right? So maybe like a 2 pointers approach type of thing, where we do if left, we'll say like r at left is less minus x is less than the absolute value of r dot right minus x. So the idea is that if the absolute value of the left is less than the absolute value of the difference on the right side, then we do add left to the list and then move left down one index, and then continue until you have k elements within the array. And then also like else do the same for the right side, adding and moving up. And then at the end, you would have, you could do this with the linked list, and that way you could keep it in ascending in order, and then you can just return the list. And then in this case, this entire approach would take O of k time, because we'd have to compare two elements and then compare the next two elements and then compare all the elements until you had k elements in the list. And using a linked list, then inserting at the beginning or the end would take O of 1 time, constant time, so we don't need to worry about that. So it's mainly just O of k time. Now, is there a better way to handle this? That is a good question. We could... I'm thinking right now of the main question for me is, do we need to actually sort the entire initial list? Well, without it, right, then we would have to do O of n to find the element. And what if we say, let that be the pivot? Then we pivot all the elements around it. But the problem is that we don't really know how close each element is to k, only, or rather x, only that it is less than or greater, right? When we do the sort of quick select sort of method of pivoting elements around a certain value x. So we know that each element on the left side is less and each element on the right side is greater, but we don't know by how much, right? So eventually we'd have to sort it anyways, essentially in order to get the closest elements. What about using heaps? Could we use a heap in any way to help us out here? Let me think. If we use two heaps, we want the root for both min heap and max heap to be x. If the value is greater than x, then add it to the min heap, because we still want the root. We want to preserve the root essentially. Otherwise move it to the max heap. So this would be for each element within the array. So this would still be nlogn. And then we would say pop both of the roots so that we don't have x anymore there. Then we can say for 0 until k minus 1, compare the tops of each element, or the tops of each heap. If the absolute value is less than other, then add and pull. And that would take, this would take O of k. Let's assume that they're even, so each of the elements have n over 2, roughly n over 2 elements within each heap, assuming that k or x is right in the middle, and therefore there will be n over 2 elements in each, and therefore this will be log of n over 2. Because we would need to remove, or we need to, when we pull it, we would take log n over 2 time each time, and we had to do that k times. So that would be the ultimate, so it would be, this would be O of n log n plus O of k log n, essentially. We can just drop the constant, I think. Time and O of n space. This would be O of n log n plus O of log n to search for the element, then O of k space. Then this would be O of 1 space because we don't really need to store anything besides the auxiliary, or besides the output. Okay. But yeah, this sort of two heaps thing is similar to a hard problem. It's like find median of data stream. The idea is that we sort of preserve the middle part, the median part, and that's sort of what we're doing here as well. Sort of we use our x as a pivot, and then we sort of add things to the left or the right of it, and we want to maintain like the min of the left, or the max of the left side of elements smaller than it, and the min of the elements larger than it, right? So that's what we do there. Though I don't think actually it's more efficient than the method of just sorting and then using like a 2 pointers approach. So I think that's what I'm actually going to end up doing. So let's go ahead and actually do that. Let's go ahead and do not the brute. I guess this isn't really a brute force solution because ultimately the time complexity is roughly the same. So let's go ahead and do that. So we can say r.sorted or sort. I think this does it in place in O of nlog n time. Then we can say val index item x index is equal to dot binary search, and we want to search for x, and then we can say val return list is going to be a linked list of integers, and we can just return that return list, and then we can say while return list dot size is not equal to k, we'll initialize our left as x index minus 1 and our right index to x index plus 1. And then we can say if left, we can just do left and right, not necessarily left and right index. If array at left index, we could do get or null in case it's at the end, right? And array.get or null right is not null either. And this should just be left. And this is else if get or null on the left is not null, and so this is if the left side is not null, and then this is if right is not null, left is not null. And then we can say, okay, so if both of them are not null, then we need to do comparison. Otherwise, in this case, we can say while left is greater than 0, or greater than or equal to 0, we can say our return list dot offer head array at left. I think, let's see, linked list documentation. Let's take a look at, because we want to add it to the beginning. Offer first is what we want. And then we want to left minus minus. And then we can say while right is less than array.size, return list.offer last array.right, and we can do plus plus here and do minus minus here. And then we can just do like a circuit breaker. So in case both of them are get or null, or if left is less than 0 and right is greater than or equal to array.size, then return list. So this is just a circuit breaker in case we don't have enough items. Though this shouldn't happen because of the input, but we should just be a little bit careful there. Of course, we also have an edge case here to think about, where if x is equal to, or sorry, if k, so if the number of elements that we want, the k closest elements, is equal to our array size minus 1, then we can just return our array dot to list. Is that a thing? Let's see, int array. This returns an int array to list. Yeah. Because if we have k closest elements where k is equal to array.size minus 1, we need to include all of them anyways. Though I guess in that case, let's see. Let me think. Let me look at the examples. So we could include the index here, right? We could include the index here, so we can say while left is greater than or equal to 0, and right is less than array.size, else if left is greater than or equal to 0, and right is greater than or equal to array.size. Just to shorten things up a little bit. And yeah, we could include the index here, so, or the original value k, although k does not necessarily need to be, or x does not necessarily need to be within the array, right? So yeah, let's see if x is -1. X can at most be -1. So we can say if right is greater than or equal to 0, otherwise we just do right plus plus, right? So this is in case the right side is less than or equal to, or the right side starts at -1 at our index here, because it would fit in the, because it would fit at the head of the list if we do a binary search for it. That means that the index that is returned by this binary search method will be -1. And then I think we should do something similar here and say if left is less than array.size, then we do this. Otherwise, we do left minus minus, because there's a chance that if binary search, or if x is greater than all elements, then x index will be array.size. And if x is less than all elements, then x index will be equal to -1. So we need to do this just in case. Or actually we could do this. If right is equal to -1, right plus plus, and then we don't need to do this part at the bottom, because this will be the only situation where that happens. Let's just grab this comment here just so we clarify this for ourselves. So this is the only situation where right would not be valid, I believe. Every other time right should be a valid index. And then same thing here. So if left is greater than or equal to array.size, left minus minus. Or we could just do left is equal to array.size -1. So that way we just know for sure, because in case that it goes a little bit wacky, though I don't believe that the binary search the binary search will go beyond, or at least I don't believe it should go beyond the level, either the array size or 0, or -1 rather. So let's just make this a little bit just more future proof, even though it shouldn't, but just for the sake of doing so. So while the left side is greater than or equal to 0, we will offer first the element and then move it down. And then we will also do the same thing for the right side, but we increment it instead and we offer it to the end because we have an element within, or we have a sorted array. And then we can say if math.absolute value of array at left minus array at x index is less than math.absolute value array at right minus array at x index. Otherwise, so in that case, we want to do return list dot offer first at array at left minus minus. Otherwise, that means that this is either untrue. Let's see. Else if math.absolute value at array at left minus array at x index is less than the math absolute value at array right minus array at x index. This should be equal to and array at left is less than array at right. Well, actually, this should always be the case. So this should be less than or equal to, actually. We always want to go with the left side. And then in that case, then we can just do return list offer last array at right plus plus. And then that should work. So this covers both less than case and equals because we want to bias towards the left index. So that covers both of these cases. So either the absolute value minus x is less, or if they're equal but a is less than b. Right. And then otherwise, then we add the right side instead. Okay. And then this is the O of k time to actually check things out. And then of course, if we have one of them hitting the edge before the other, then we just go for the others. And then also the edge case where if k is equal to our size, let's see. Well, let's say if k is equal to our size, right? Then we can add all of them. If we have k closest elements to the element, then it really doesn't matter how we want to include them. So I think this should work. Let's see. So we sort it, then we do a binary search for it. So this is binary search, which is O of log n time for the element, or where it should be. Then we do a return list, we do a left and right, and then we do a 2 pointers approach where we sort of check each pointer to see which one is closer. And then we just go ahead and continue checking. If they are both valid, then we check and then we move the pointers appropriately. Otherwise, we just start adding in all the items. And k is less than array.size, and we should do this so we don't accidentally break or we don't accidentally overfill the outside while condition, right? So we need to make sure that k is also less than the array size. Then we just do that, and then we also have a circuit breaker in case we don't have enough items. So if both of these are invalid, then we will stop, essentially. So if the left side is less than 0 and the right is greater than or equal to that, then we just return the return list as it is, and then we return the return list at the end regardless. Let's go ahead and run this. Okay, so it looks like it worked for the first example. Let's go ahead and toss in the second example. Oh, it looks like we missed an output. Let's see. Turn this to size, not k. Well, we want the 4 closest elements to -1, right? Oh, interesting. Let's see where we went wrong here. So I had k is less than array.size. Oh, k is less than array.size. No. K is less than return list.size. K is less than return list.size? Yeah, that's fine. Though it should be really less than k, right? Yeah. Okay, cool. So the second one worked. Let's go ahead and just recheck the first one, just to make sure that we didn't do any regressions. So I think this should work. 10 to the 4 generally means O of nlogn I think should be acceptable. 10 to the 5 is when, I think for LeetCode problems, when it seems to suggest a linear runtime. But I think this is fine. I'm not sure if there's any way to go faster than this, because you kind of need to know like the closest items. And I don't think you can do a quick select here because you need to know exactly how close or what the closest item is. So you could either use 2 heaps or you could use 2 pointers and sorting. Either way, it's at the least, or at the least it's nlogn time, right? It's bounded by that mainly. So let's go ahead and run a submit and let's see if we're actually fast enough or if there are any changes that we need to make. Let's see. It looks like we ran into an issue here. 9. And we outputted 1. Interesting. Let's see. 1, 1, 1, 10, 10, 10. We want the first closest element to 9. The index should have been 3 and 2. And the difference is not the same. The difference is not the same. Clearly, there's one that's larger. I'm curious as to why this didn't add in 9 or add in 10 rather than 9, or rather than 1. Let's quickly check. Alright. The left side should be 1, the right side should be 10. Well, return list size is less than k. If left is greater than 0, so this didn't actually get triggered at all. Let's see. Shouldn't be this, because then this wouldn't be added. less than k. The size starts at 0, right? I don't think I added anything to the return list in the beginning. If left is greater than or equal to 0 and right is less than array.size, that should trigger. Let's see. If this doesn't trigger, then that means that this is breaking it. This edge case. -5 and -4. Oh, is it because it's not in the list? In that case, if x index is less than 0, let me think. That's interesting. Okay, so it doesn't exist. So what we need to do is kind of do this. So var index is there. So if x index is less than 0, then x index is equal to not x index. How do I do a negation, binary negation in... It's just not x index plus 1, I think. Bitwise operations. Oh, it's inverse. I think it's this. Invert that plus 1. And then let's run the code again. Interesting. Yeah, I kind of forgot about this. Big integer. Oh, I don't want to do that. Is this like a... I know that there was an issue with this before, I think. How did I do it in the other problem? I remember there was another problem where I needed to do... It was a patience sorting one. Longest common... Sorry, longest... Yeah, longest consecutive subsequence? Something like that. Let's see. Yeah, that's not working. Interesting. Looks like it wants a big integer, which is not really what we want. I wonder if this tilde works. I don't think the tilde will work, but we'll see. Yeah, what INV? Oh, we need to do this dot .inv. There you go. That should work. And let's see where what the indices are now. Yeah, 3 and 4. So 0, 1, 2, 3, and 4. Let's just make sure that these are still the same. So 1 and 2. Or, sorry. Left is 2. Right is 3. Yeah, index 1 and 2. But we're looking for 4, right? Or is it from 3? Oh, x is 3. Okay, yeah, so that makes sense, yeah. Then we want to do similarly for the bottom one. We start at 0 and 1. And then we just start from there. Though I think actually with that part, Oh no, you could still have overflow issues there. Okay, yeah. So I think this will work. Let's go ahead and run a submit now. So just a little bit of an inverse here. Check. Output is that. Interesting. Let's see. So we added 3 ones. 2, 3, 6, 7. And we wanted 4. Let's see. So we started at probably like here. Or actually probably here, right? 2 and 3. So 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4, and 5 indices. And then we would check the... So we would probably add 2 first, then 3. Then comparing 1 and 6, it should be 1s all the way. And then 6, 7, 8. And then we compare 9 and 0. Interesting. Let's do a print line and let's check. Print line array at left, array at right. We need to wrap these in curly braces and the $sign. So we should be comparing 2 and 3, then 1 and 3, 1 and 6, 6 and 7. It would have gone there at 0, 1, 2, 3, 4, 5, 6. Actually, I don't know why I'm doing this. Should be doing this instead. Not R at index, just X. 6 and 7 though. Interesting. Because the index of the 4 would be in this spot where the 6 is, and that should be the right index, but for some reason we're scooted 1 over. Interesting. I wonder if that will heavily affect us. Really not sure if that'll affect us or not. I don't think it should. But it might affect us. But yeah, no, I should have been comparing against our actual x value rather than the index or the number at that index. Okay, everything seems to be fine, even though our indices are a little bit off. Maybe there's a way to, or maybe we should adjust our index a little bit more. Still getting a wrong answer. Interesting. Wonder why that's wrong. Let's see. It would start at... We would probably start the number at 4 and 7, right? Or would it be 7 and 7? Interesting. That's the 2's complement. So we start here instead because it doesn't exist. 7 is not okay. So if we want to do this instead, left is equal to x index minus 2, and the right is equal to x index minus 1. That doesn't seem like a great solution. Like, it works, but I'm not sure if that works the way that we really want it to for all cases. Like, it'll probably work for cases where it doesn't exist. And then I guess for the cases where it does exist, it doesn't really matter as much either. So I guess this is fine. I'm just gonna check all of these to make sure that I don't run into any regression testing. Yeah, that's weird. Because this 2's complement should be the same. Like, the 2's complement shouldn't affect it in any way. Still should just be the inverse of it. But for some reason, it's like 1 above what we actually want. It's interesting. I'm not entirely sure what's going on there. Maybe there's a mathematical explanation behind it. But yeah, that's it's a decent runtime. I think it's might just be plagued by some issues that we're having. In any case, I think this is a fine solution. Like, any adjustments would just affect the percentage, but not necessarily the asymptotic runtime, I feel. I could be wrong though. But in any case, we used a sorting, and then we used the sort of 2 pointers approach in order to get around to the closest elements. We had to do some finagling with the indices, which I'm not super happy about, but it happens. In any case, I hope you learned something, and I'll see you for the next problem.